Okay. Hello, everyone. I'm Minglan Yu from Harvard University. Today, I'm hosting the one talk in the P4 workshop. This is about the one big switch abstraction using P4, and it will be presented by JK Lee, who is a principal engineer in Intel Barefoot, and Petr Lapukhov, who's a network engineer at Facebook. Yes, JK, please.
Okay, thank you, Milan. Let me briefly go through the agenda and then hand it over to Peter. So yeah, Peter will talk about the kind of customer view, why we need such a high performance cluster with one big switch abstraction, particularly using the machine learning training as a motivation workload. And then we will talk about our vision statement. So what is the one big switch, and then what the distributed VOQ abstraction on top of this one big switch can help us in terms of realizing the performance abstraction we need for such a challenging workload, and drill down to some more about detailed problem statement, like what kind of network conditions are there and how can we handle them by using some of the switch side building blocks, and what P4 constructs are there to help us to get there. Some materials in this talk based on some contributions from my colleagues, and then these are the names that contributed to these contents. All right, then Peter.
Thank you, JK. So folks, this diagram is an illustration of what we call a training cluster. This is what we typically use to train large ML models. On the diagram, you can see there are two fabrics where we plug these specialized nodes, which consist both of accelerators and CPUs. The accelerators, you can imagine, are typically GPUs or something along these lines that can perform the intense math that we need for ML. And I think the most important part about this diagram is that every node has, in this instantiation, 8 accelerators and 4 CPUs, and they connect different fabrics using different NICs. The so-called front-end NICs are regular, as you call them, dump or ordinary NICs, which we use primarily to ingest data from the storage for ML training. And data can be, let's say, images or impressions or whatnot. And for the backend NICs, we use right now the RDMA offloaded NICs to allow communication between the GPUs. So this is your cluster that can be typically as large as a few hundred nodes, well, to more accurate, a few hundred GPUs. And the fabrics on both top and bottom can be different closed networks. Next slide, please. Just a few details on distributed ML training. I won't go much in details about how things work because lots of papers out there. But in our case, the models that we employ combine both data and model parallelism, which means the trainers have to pass lots of data between them and at the same time ingest a steady feed of examples. You can call that what we use for training is the instantiation of bulk synchronous parallel model, or BSP, which is well known in the community as the model for parallel computations. What's so special about this model is that it gives rise for special collective communications. The trainers in the cluster have to exchange data in specific synchronized bursts of data where we realize specific collective. A collective can be a data exchange like lookups or a gradient exchange and so on. What's most important is that at every training cycle, all of the trainers have to arrive to a barrier before we continue to the next cycle. I also put a link on an archive paper that provides more details on the reference workload that we use at Facebook. Next slide, please. And now to a problem statement. As you can imagine, in a synchronous parallel training, you have a computational phase and I/O phase. In our case, they interleave. So it's compute phase, I/O, compute I/O. And that cycle is over. During this training cycle, the trainers issue the different kinds of collectives. That could be all-to-all or all-reduced, being the most common. And that, to be precise, is what differentiates the ML training from general HPC applications. In the HPC, you see usually wider variety of collectives. In ML, you have just a few types which you repeat very, very often, many times. Of course, every combination, every collective produces a combination of network flows. And the goal is on every cycle to minimize the completion time for collectives, because the training are synchronous and your performance is determined by the completion of a last collective and this last flow. I also want to highlight that unlike the HPC applications, what we see right now at the moment is that most of the messages are pretty large, like 1 megabyte at least for the all-to-all exchange, and even larger for all reduce for gradient exchange. And it's also a specific of the ML applications. Next slide, please. And now the specific challenges that we are seeing in these topologies, right? I already mentioned we have two networks, front-end and back-end. And the back-end is the one which uses RDMA. In our case, this is Rocky. But people, of course, use InfiniBand as well, which is probably another popular instantiation. And specific thing is that the all-to-all collective is the very bandwidth hungry, right? When you do all-to-all, the performance is bottlenecked by the bisection bandwidth. That's an old-known rule, I think, from the days of MapReduce, where people used all-to-all as the benchmark of the network. All-reduce traffic is interesting. It doesn't create as dense of a patterns as all-to-all. Like a classical scheme for all-reduce is to have a ring topology for communications, but it has lesser flows. So if you use a naive network with ECMP, you may end up lots of flow collisions. So you get into the classical ebb and flow problem, right? Additionally, because of the all-to-all all-reduce overlaps, you may run into in-cast issues in some of the simulations, not simulations, but some of the actual runs we've been running. And lastly, but not least, is that we began with a smaller topologies, and as we start to scale them to a larger closed fabrics, we realize, and I think it's well known, you have to put lots of efforts to tune Rocky to work efficiently at this scale. And so funny enough, when we began this experimentation, our fabrics were just one switch, like one crossbar switch with many ports, which used to work just fine. Well, obviously, because the internal fabric of a crossbar switch is pretty efficient in modern switches, it has the queues, it has end-to-end scheduler, and it allows Rocky to work seamlessly without any problems. But I think the challenge we realized is to try to scale and go to a closed, larger fabric, we start seeing lots of issues in terms of performance. So I believe that's what motivates our need to go to like a model of a large virtual output queuing switch. And now on to JK for the rest of the slideshow. Thank you.
Thanks a lot, Peter. All right. So it was a really nice transition to our vision statement. Yes, we want to have performant one big switch abstraction on top of the entire network. And many of you probably heard about one big switch abstraction network as a one big switch model a lot, especially from maybe SDN, when the network-wide programming of the control plane and policy has been on top of this large network as a switch abstraction. And of course, network virtualization like OVS, OVN is hiding and abstracting out the physical network as a one big switch. And more recently, service mesh is used to connect the microservices in layer 7 on top of the same abstraction. And what it is basically, yes, we do have a very complex, maybe class and factory topology with lots of switches, but at the end, all of them are abstracted out as just one switch, and where all the servers or compute nodes are connected through this kind of host, which guarantees the bandwidth, transmission and reception bandwidth for each compute node connected to this model. And the model itself, which is a non-blocking fabric. So there is no congestion or blocking happening within this switch model. So as a result, the congestion happens only at the network egress or the output queue, connecting the entire switch abstraction down to each individual receiver. And as Peter mentioned, that there is also a pretty well-known concept of virtual output queue, which is a mechanism to push the location of queuing from the output queue to the input by having some signaling from the output to input, and then so that network, the switch ingress can do the queuing at the input layer based on the information provided by the output. But now the reason why we are calling this distributed VOQ is that in the one big switch model, it's not really one physical switch. We are talking about the fleet of network switches. So the network egress side congestion and then bandwidth information has to be communicated to the ingress. So the ingress can, the VOQ abstraction in the ingress can correctly reflect such a egress side congestion information or bandwidth availability information. So where we cut the boundary and where do we define the ingress of the one big switch, whether it would be first hop switches, physical network, or it could be senders. That's a very interesting question we are currently looking at. And then the rest of the slide, we'll talk more about the maybe ingress and egress switches, or first and last hop switches as a boundary as of today, but we really want to push it out. So let's talk about this. So realizing that performance and one big switch abstraction has a couple of challenges, basically congestion. So there are different types of congestion. One is unlinked core congestion caused by inefficient or ineffective load balancing mechanism. The granularity is too large, so the elephant flow collision can always happen. And it gets worse when the network is oversubscribed. And as also Peter mentioned, we may have a many-to-one incast pattern, which can cause kind of surge of congestion or queuing delay at the last hop switch, or kind of PPS level of incast or congestion can also happen at the receiver NIC. So the incast, when we talk about in the network level, is more about BPS level congestion, lots of bytes trying to be transmitted to the same receiver. Once we survive, the startup package survive the BPS bottleneck, it may be composed of lots of packets. So such a high IOPS or PPS may cause the receiver NIC side congestion. And both of them are kind of motivations and challenges for VOQ, because this type of incast or congestion happening towards the last has a really, they may not happen that often, but when they happen, it can cause a pretty large delay. And then the thing is that existing end-to-end congestion signal loop itself can be delayed by this ongoing large congestion. So that's where kind of realizing VOQ abstraction with instant signaling is more interesting and important. So what we can do at the switch first, the reason why I'm talking more about switch is that currently we do have some examples of fully programmable switch data planes. Of course, we definitely want to be able to design the end-to-end correctly. But for now, in this talk, let me talk a little bit more about the switch side building blocks and how we can help actually the end-to-end design. So first, the switch can provide the rich and accurate congestion information for the applications or transport our NIC can consume and then adapt to it very fast. And secondly, for the non-blocking full bisection bandwidth, of course, the network oversubscription better to be one, basically, but still the fine-grained load balancing, which guarantees no out-of-over delivery or minimal out-of-over delivery will be great. And for the signaling of the egress congestion information to ingress can be achieved by something like a cut payload as NDP has proposed, or we may think about some SubRTT signaling back to senders from the ingress side of the congested switch. And they can handle such a sudden change of the congestion or link status faster than the end-to-end congestion control signaling. And finally, when the receiver NIC is congested, ideally we would have some intelligent smart NIC which can, or the receiver side software solution which can handle it. But until when we have such a fully programmable smart NIC, we may still leverage some switch programmability to help out this problem. So this is the list of kind of congestion-related metrics the switch can generate and then provide. There are lots of dimensions we can talk about, which data or control packet we want to react to, or what information, queue depth or draining time or available bandwidth or in-cache ratio. Many of them can be provided and in different ways, either inbound to the forward direction packets or separate packets sent back to senders, or signal to the receiver like NDP cut payload does. And having such information provided from the network ingress versus egress has a different meanings in terms of the location of those metadata and also depending on the use cases. And especially when we generate such a separate signaling packets, we want to be cautious about not to causing too many signaling overhead and for PPS or VPS overhead. So having some intelligent mechanism to determine when we want to generate such a signaling is very important. So there are lots of P4 primitives that we can think about. We don't need to go through all of them. I think few highlights are something like a standard and intrinsic metadata already available in PSA or Tofino native architectures are great starting points to provide such a metrics. And using some register and also MIRO or LPF externs, we can generate a bit more higher level and then more meaningful metrics for the congestion control and transport to make use of it. And we can also think about different type of actions like a modify, mirror, recirculate, multicast actions as a way to generate the signaling packets and then transport out. And in the last year P4 expert roundtable talk, I was able to talk about the ingress side visibility of egress queue status. And then it can also accelerate the generation and then signaling of such a congestion information in the better location. And in terms of the intelligent conditions for generating such a signaling packets, we do have also register and meter externs, and also we can easily also make use of something like a PFC frame received from the NIC and then process them in the switch side P4 pipeline and then make a reaction. If you want to react to, for example, the receiver NIC congestion and then generate signaling packet also from the switches. Secondly, for the non-blocking fabric, yes, fine-grained load balancing is crucial. There are multiple ways to achieve this goal. I'm not really promoting any particular direction. The NICs, sender NIC can actually do some packet spraying on top of the existing ECMP fabric by tweaking maybe UDP, the source port number, or adding a little bit more other entries that can be used by ECMP hash. And it's been deployed by AWS based on their announcements. And another alternatives we can think about at the switch side is either flowless switching, like Conga, or kind of per packet spraying, but something like a deficit round robin can be easily implemented in P4 as an effort to minimize the load imbalance and consequently also minimizing the out of order delivery window. It has a pros and cons. For the sake of time, I'm not going to the details, but we'll be happy to talk about in the Q&A. Yeah, we briefly talked about cut payload as a mechanism to signal the last stop switch congestion to the receiver. And there is actually a separate talk by Rong and Reshma. So yeah, please check out that talk and you will learn more about this. And finally, we do have some prototype implementation of the SubRTT signaling between switches. We can think about, so this is kind of simplified diagram where number of hosts are sending for this one receiver host. This is kind of typical in-cache scenario. And then the last stop switch where it's experiencing the in-cache congestion can actually detect that when the congestion information even when the packet is being processed, ingress pipeline of the switch, and then signal it back to the senders. And today, because we don't have such a intelligent sender NIC side changes, which can make use of the information, as a kind of stopgap measure, we are using existing PFC as a mechanism to instantly pause the sender flows at the sender NIC. But obviously, our future work is to introduce more fine-grained, let's say, per receiver virtual output queue abstraction, so that we can do more fine-grained reaction and then, to this kind of congestion signal. Let me fast forward the animations. I briefly mentioned that the receiver side congestion can be signaled maybe through PFC also to the last stop switch, and the last stop switch can also make use of the information to generate such a congestion signal even before the egress queue towards the receiver is being congested. So many things are possible thanks to the P4 level programmability. This is a simple demo we created. So let's say we have a number of hosts sending to these two different receiver nodes, and then we created a multiple bottleneck points between these, one between these two switches and also the links toward the victims. As a result, when we do PFC, for example, for regular Rocky, then the PFC can back pressure, and then it may create a head of line blocking in the inter-switch link. But when we have such a source flow control like a edge-to-edge signaling mechanism, then you can avoid such a head of line blocking happening between the core links. And then the senders can be paused as a reaction to the congestion happening at the remote switch. So that's a high-level idea, and we do have a simple flow completion time comparison between PFC versus SFC. Currently, the gap between them is not that large because network scale is relatively small. And when we simulate in the larger scale, the gap between them can be go over order of magnitude. And this is the actual measurement from the switches comparing the Q depths between PFC and SFC at different points of the network. At high level, yes, the Q depths or the buffer consumption at the switches are maintained relatively very small, while we are providing such a faster flow completion time. All right, this is the last slide. This talk is about one big switch abstraction. The community has been looked at for a long time, for a long time, and we are saying that the one big switch abstraction with performance guarantee is possible thanks to the recent P4 programmability and primitives. And we nailed down to non-blocking class fabric plus SubRTT signaling to realize such a BOQ abstraction. And the remaining research questions or maybe engineering questions for us is that how do we really realize the BOQ and where do we cut the boundary? I think it depends on what is a major incast or congestion bottleneck point, and then the scale of virtual output queue that we have to maintain at the sender. I will stop here and then we can go into the Q&A.
Yes, thank you for the excellent talk, JK and Peter. And this is a very interesting talk because we have both the Facebook side, the application side with requirements, and JK from the Intel Barefoot as the vendor provider who provide features for us to meet these requirements. So I would like to start a question for Peter, which is, you mentioned there are a lot of problems when we move from a single switch to many switch network of running machine learning jobs, especially in Roxy setup. What specific performance problem do you see there?
Just to recap, with nothing dramatically new, right? So when you do this closed fabric, you face two problems: efficient routing and congestion management, right? As usual, and it's especially alleviated by the fact that Rocky is purely in hardware, so you can push a lot with line rate, and the control logic in Rocky is somewhat custom. It's not like standard. People can tweak things there on their own. And the schemes to manage congestion typically revolve around tuning PFC and ECN. So most of the time, people spend tuning these settings for PFC and ECN to make sure we get some performance acceptable under incast, right? Like incast test is our typical stress test we use to verify performance of a particular scheme, and you have to factor things like given cable length, right? To size the PFC buffers, right? The headroom buffers, and ECN thresholds, and things like contention on the egress port, which causes like cutoff line blocking. But the net result is that some collectives, if you exhibit pretty intense like incast, can perform very poorly, right? Because your tail time deviates very heavily from average time. So it's a well-known problem. Like collective completes slow because of one or few outliers. And unfortunately, unlike in the web applications, where if you lose one flow, you're okay, you can continue computation. In this case, if you lose one flow, you have to restart full collective, right? Because you need all the data to complete this. And observation we have right now is that major bottlenecks coming from all-to-all exchanges, because they are often most incast heavy in terms of like traffic flows, and they require pretty heavy bisection bandwidth. So in some sense, as I mentioned, we are back to square one. We had MapReduce, which had all-to-all flows because of the data hashing and extraction. Now it's incarnation in a sort of co-flow model where we have a collective.
Okay, thank you. And with the requirements clear, then I think follow-up question for JK would be, I think you provide a lot of important primitive switches that to help congestion control and mitigate incast. I wonder, do you see any special improvement like these primitives together could help machine learning training, or is there any like customization you would recommend that our target application ML training jobs? Like which of the primitives may be more useful?
I see. Well, I think this is a very interesting problem that we all together as a community, or Peter and I, as our two representatives, to think more and then design. And in a way, such that I'm trying my best not to say that as a Intel, I don't think I have all the answers, because the customers knows their problems the best. And each network owners, and now there are many different, even for the machine learning training cluster, maybe beautiful Facebook might have its own unique, I think, characteristics, differentiating from maybe some other machine learning clusters, and nailing down and customizing for each customer or network characteristics is something actually I'd like to let the network administrator and owners and designers to actually own and then build. Yes. Thanks to this, all the programmability we are now providing at the switches, and now actually expanding towards the NICs and also software-based packet processing engines. But I think the good high-level question, and then going back to the Peter's statement about multiple problem statements, I think first, the reason why Rocky is really hard to tune is, I would say, mainly contributed by the fact that the condition signal is not timely and not accurate and not really precise. It's just a 1-bit binary signal. And even if there is a multiple ECN marking happens, that receiver Rocky NIC kind of filters out low pass filter, and sender can react to ECN around 1 ECN to the ECN condition signal per RTT. It's not really give you very instantaneous condition information when the link state changes very fast, especially with this incast. And if you now think about 400 gigabit per second link speed, even just 10 to 1 incast is relatively small. We are talking about 4 terabit per second of traffic, right? It's a huge. So providing such a rich and condition information or bandwidth metrics as soon as possible to the transport, either receiver and sender, is very important. And that's why we actually try to nail down these multiple building blocks the switch can do. Mostly signaling in terms of this number 4 and 3 to 5. Number 2 is a little bit different because it's more about active load balancing switching can do, but still there's a mechanism that sender NIC can do simple, I guess, source port shifting, randomization, and the switches can still do the ECMP. There are multiple different ways. I'm not trying to promote any particular solution.
Yes. Yeah, go ahead.
Sorry, I can also add one thing which seems to be important in conversation. The use of Rocky as the transport. You can always say, hey, why don't you use HPCC or NDP or HOMA? All the wonderful ideas. The challenge we face is that it's hard to change all variables at once, right? And in some sense, we have to operate with what market is having for us available. In some sense, Rocky is what is de facto standard for the communication between accelerators because it happens to work great with things like GPU direct and peer-to-memory access, right? So we have to say, okay, we have to keep something invariant, but then try to optimize what's possibly easier to tune. And comes out tuning network is a bit easier than the software stack on the NICs, the firmware stack. And just to add up to JK's, I think the two most important primitives would be anything which relates to adaptive routing, allows you to pick up paths based on the load. So it's a well-known idea from the HPC days. Adaptive routing, especially in class, it's much more straightforward. Although, like if you look at Conga paper, even realizing the remote sensing congestion is non-trivial, right? You have to know what's the congestion on the other side of the link of a fabric. And second one is this more precise, more fine-grained flow control, right? This idea, I think, is also available in a paper called BFC, back pressure flow control, right? PFC is known to be operated on just like priority levels, right? At the port level. If you can have anything more fine-grained, you naturally result into much more efficient rate management, right? So think about this, a problem, a solution, it has two components, routing piece and then sort of rate management solution, right? How do you decide the rates? And rate programming could be done by PFC, you modulate the rates, or ECM, you tell the receiver to, the sender to slow down. Sorry, it was just my 2 cents.
Thank you, that's very helpful. And JK, I want to bring back your earlier point that as a vendor, we would like to provide an abstraction like the one big switch abstraction with all the primitives so that customers can select the right configurations and right features for their own protocols and their applications. Given that, like, what is the right kind of one big switch abstractions that you think maybe making it easier for customers to use? For example, it has two parts, right? One is what is abstraction for people to specify their performance? You mentioned the host model, but I guess you also did many works in the past on what is other possible models. So what is a good model for vendors to specify their performance requirements? Another is what is a good model for vendors to select and configure these parameters, these features in their setting in a high level rather than on the one big switch abstraction rather than configure individual switches, right? Yeah, just one.
That's a great question. Deserves maybe another 1 hour. Thanks for bringing up some of the performance abstraction model. Yeah, the community looked at different abstraction like tree-like abstraction or graph-like abstraction. I was trying to also provide such a best of the both worlds and fill the gap between application level graph representation and then actually physical tree-like topology. But as I understand, what really big public cloud service provider do as a network performance abstraction is like a host model still, right? Mm-hmm. And this is really simple, maybe not optimal, but at least it may be decent model for MapReduce like all-to-all communication or even this or reduced collectives. It may still work. So that's another still, I think, ongoing problem. But from the maybe P4-driven end-to-end network design perspective, to me, the one interesting question is that which bottleneck we really want to model using this VOQ. And then once this VOQ abstraction at the sender side or ingress side is representing such a different bottleneck points, then how do we make use of them? Maybe it may be something like that. VOQ just model that last of switch or receiver NIC side condition, but the way sender consumes that information and the granularity of the reaction might be more finer grain. It could be maybe per flow, per condition, or I don't know. We are still starting to explore that possibilities. Like Peter mentioned that one of the early VOQ abstraction proposed by Konga paper was really kind of confined that as a network ingress and first and last of switch. And then we are now trying to expand that. And where do we cut the boundary? I think it's really early stage. I wouldn't argue that I know the answer at this point, but there's a set of great questions too.
Yeah, these are good open questions for the audiences to explore as well. Just one last question, which is, JK, you mentioned there are incast happening not only in switches, but also at NICs. So for those, if NIC is the bottleneck in the application, what are the primitives we can, that you proposed in this talk can be useful there, and or what extensions we may need to do at the NIC to address those?
Yes, let me make it quick as possible.
Mm-hmm.
Yeah, like I briefly mentioned, the receiver NIC condition is more about PPS or high IOPS caused by them. And then if you have actually many queues, actual physical queues at the receiver NIC side, which can isolate condition to different receiver applications, it may not reserve the condition by itself, but still it provides a good isolation. Basically, flow queuing at the receiver NIC is relatively possible compared to doing so at the switch side, because switch side, the number of physical queues is relatively limited compared to the entire number of flows that the switch has to handle. So I think that is one good way to handle it, either the good design between the receiver NIC and the software infrastructure that can provide a decent isolation per application. But here, what we presented here is a kind of stopgap measure where if we don't have such a intelligent smart NIC at the receiver side, and the condition may be back pressure to the last of switch through existing legacy PFC mechanism, and the last of switch can still do decent signaling as we have shown in the later slide. So that is just one possibility, and there could be even more smarter, crazy ways to resolve that problem.
Mm-hmm. Yeah, thank you very much. That's all my questions.
Thank you very much. Great questions.
Thank you, Min-Lan. Thanks, JK.
Thank you.